Today, we will look at two proofs. One of them is an actual proof by contradiction, and the other proof is a pseudo proof. It's pretending to be a proof, but it actually is wrong. So, the first proof that I'm going to show you on the board will be Euclid's proof of prime numbers being infinitely many. For many years, mathematicians and the like have tried to find the largest prime number. In doing so, mathematicians are still trying to find the largest prime number. Computers are working on this, etc. But way back in Euclid's time, there was a proof which showed that there's an infinite number of primes. So let's go through that. Now, a proof by contradiction is a widely used method of proof. And what it does is it actually assumes the opposite of what you want to prove. And then it shows that there's a contradiction with this assumption. Okay, so the opposite of what we want to prove is that there's a finite number of primes. Okay, so if there's a finite number of primes, then we can say that there's a number A, which is the largest prime. Okay? So I can say there's a largest prime, and I can call it A. So, with that in mind, I can make the set of prime numbers composed of 2, 3, 5, 7, 11, 13, all the way up until A, according to my assumption. A was my largest prime. Okay, so this is now my set of primes. 2, 3, 5, 7, 11, 13, all the way up till A. Now, think about this number that I'm going to write down. I'm going to call it T, and I'm going to say T equals 2 times 3 times 5 times 7 times 11 times 13, all the way up until A plus 1. Okay? So I've got this number T, which is the product of all the primes in my set plus 1. Now I ask myself, what kind of a number is T? Is T divisible by 2? No. When I try to divide it by 2, I get a remainder of 1. Is T divisible by 3? No. I get a remainder of 1. Is T divisible by 5? No. I get my remainder 1 again. So what can I say? T is not divisible by any of these numbers in my set. So what can I say? I can say T is prime. But clearly, T is bigger than A. So, there's my contradiction. I assumed that the set of prime numbers had a largest number. It was finite, and I just showed a contradiction. I got a prime, a seemingly prime number, which was bigger than my assumed largest prime, A. Therefore, I go back and say, my initial assumption of the opposite of what I was set out to prove must be wrong. So there isn't a finite number of primes, there's an infinite number of primes. Hi, welcome to the proof of 1 equals 2. All right, so here we go. Let's start with A equals B. Then we'll multiply both sides by A to get A squared equals A times B. Then let's subtract B squared from both sides. We'll get A squared minus B squared equals AB minus B squared. The left-hand side we can factor as a difference of two squares, so we'll get a minus b times a plus b. And the right-hand side will factor as b times a minus b. Notice that we just factored out the b, which is the common factor on the right-hand side. Now we can cancel both sides by a minus b, and we'll get a plus b equal to b. The next step is to substitute b for a on the left-hand side. So you get b plus b equals b. Combining like terms on the left-hand side will give you 2b equals b. Then when we divide through by b, we get 2 equals 1. How is this possible? Something fishy went on at one step, and I just glossed over it, but it was an operation you couldn't do according to algebra. So why don't you pause the video now and try to figure out which step that was. Give you 5 seconds to pause the video, and then let's see if you can get that step that was not allowed. Okay, here comes the answer. Remember when I said we're going to cancel by a minus b both sides, right? And then I just went on to the next step. I was actually dividing by a minus b both sides, but a minus b is 0, right? Because I started out with the assumption that a equals b. And you know from your previous work that you can't divide by 0. And after this step, actually, everything that goes on is fair game. I mean, I could practically get anything. I could get 1 equal to 5 or 2 equal to 3. Because I performed an operation that was not valid. Okay? I hope this proof is useful in actually telling you that you can't divide by 0. Okay? It serves as a reinforcement, if you will. Thanks for listening.